So now let us define the next notion of what is called as the null space associated to a linear transformation. So this is a definition of a null space. So let T from V to W be a linear transformation. Then the null space of T. So let me just underline what is being defined. Null space of T denoted by null of T is the set. So let us see what the set is. Null of T is defined to be the set of all V in capital V such that it is a subset of V in particular such that TV is equal to 0. So the null space of T is the collection of all those vectors which are killed by our linear transformation T, or in other words it is the collection of all those vectors in V which are mapped to the 0 vector of W by T. So let us just scroll up, look at our examples and see if we can say anything about the null space. So what would be the null space here? So let me just mark it in green. So here the null space is the null of T will be the entire vector space V. Every vector is being sent to the 0 vector here. So it is the entire vector space, right? What would be the null space in the case of the identity map? So let us see. It is the set of all vectors V in capital V such that IV is equal to 0. But IV is equal to V. So this forces V to be equal to 0. So the null space here is just the 0 space, the 0 set, right. What would be the null space here? The null space will again be the collection of all elements x such that m times x is equal to 0. But if m times x is equal to 0, because m is non-zero, okay, m not equal to 0, let us put this condition here. Because if m is equal to 0, it will just be our 0 transformation, linear transformation. We have already seen that example. So let us only look at non-zero linear transformations in this example. If m is non-zero, mx is equal to 0 forces x to be 0. So here null of T will now again turn out to be just the 0 vector. The same would be the case, you should check that's the same case in 4 as well. The null space is just the 0 space, 0 set. I'm using the word space, I am coming to that in a minute. This will also be actually linear transformation where the null space is just the 0 space. Yeah, it is not actually maybe I should have given some more examples where, yeah, this actually is a good example, but I will not go into details here. The null space of the linear transformation T, which is given in example 6, will be all those vectors in Rn which when multiplied by a given matrix is equal to the 0 vector. So we will see that later. We will certainly revisit this example. We will see that if A is an invertible matrix, the null space is going to be the 0 vector. If A is not an invertible matrix, the null space will be some subspace, in fact, subset of Rn. The case when we look at 7, the null space, what are the polynomials which when differentiated give us the 0 vector or the 0 polynomial, the constant. So the null space here is the set of all C in P of R, in C in R, all those constant polynomials. Whatever the null space turns out to be, one thing we can certainly conclude is the following lemma. Null of T is a subspace, vector subspace of P. This is actually quite straightforward. So, let V1, V2 be in capital V and C be in capital R. Then, not in capital V, let V1, V2 be in null of T and C be in capital R. Then, what is T of V1 plus CV2? We want to show that null of T is a, just 1 minute, let me not make unnecessary mistakes. So, let V comma V1 comma V2. So, T of V1 plus V2 will turn out to be T of V1 plus T of V2. But we know that V1 and V2 belong to the null space of T, and therefore, T V1 is 0, T V2 is 0, and therefore, 0 plus 0 will give you back the 0. Similarly, look at T of CV. This is equal to, by the very property of a linear transformation. So, the above one was also because of the fact that T is a linear transformation. This will turn out to be CTV, but TV is the 0 vector, and C times the 0 vector is again the 0 vector. So, the first one implies V1 plus V2 belongs to null of T, and this implies that CV belongs to null of T, and therefore, null of T is a vector subspace. Let us prove the following proposition. A null space is not some arbitrary vector subspace. It is a subspace which captures some information about the given linear transformation. So, let T from V to W be a linear transformation. So, remember that V and W are vector spaces and W is not necessarily a subspace of V. So, T from V to W be a linear transformation. Then T is injective if and only if null of T is equal to 0. So, the null of T being 0 captures information about whether T is injective. So, this is an if and only if statement. So, let us give a proof of that. In many of the examples that we gave above, we saw that the null space is 0. It is quite easy many times to check whether the null space is 0 or not, as compared to checking whether T is injective. So, in many of the cases above, we saw that the null space was 0. In all those cases, T turned out to be an injective map. Right. So, let us give a quick proof of this. So, in this direction, we will assume that T is injective. T is injective. Then, let V be an element in the null space of T. We will show that V is necessarily equal to the 0 vector. What is the meaning of V being in the null space of T? This means that TV is equal to 0. But we already know that the 0 vector of V should necessarily map to 0, and therefore, this is equal to T of 0. This implies V is equal to 0 because T is injective. So, if we start off with some vector in null of T, we see that it has to be necessarily 0. So, this implies that the null of T is 0. Okay, that was quite straightforward. Let us look at the other direction. As it turns out, the other direction is also equally straightforward. So, assume that null of T is the 0 vector. Then, suppose V1 and V2 are two vectors in V such that TV1 is equal to TV2. Our goal is to show that T is injective. So, we will take hold of two vectors V1 and V2 such that TV1 is equal to TV2. We will conclude that V1 is equal to V2 from that. This, however, implies that TV1 minus TV2 is equal to the 0 vector by adding the additive inverse of TV2. Now, this is an exercise for you to check that this TV1 minus TV2 is nothing but T of V1 minus V2. Just need to check that T of minus V is equal to minus of T of V, which is the case. But this is equal to our 0 vector as noted here in star. And null of T we know is just the 0 vector here. This implies V1 minus V2 is the 0 vector, which implies V1 is equal to V2. And therefore, our T is injective. So, this completes the proof. Yeah. So, maybe I should give an example in Rn. It's actually quite straightforward to give some example. Let's look at a map, say T from R3 to R, where T of x1, x2, x3 is equal to x1 plus 2x2 plus x3 equal to x1 plus 2x2 plus x3. Then observe that what is this, so this check that this is a linear transformation. So, as I said, we will keep giving more and more examples on the way. Check that T is linear transformation. And okay, maybe we should look at the example where this is x1 plus x2 plus x3, because we then know exactly what the null space would be. Then null space of T is the set of all x1, x2, x3 in R3 such that x1 plus x2 plus x3 is equal to 0. If you go back to maybe 2 or 3 lectures back, we had actually explicitly studied this vector subspace of R3. In fact, we had even computed the basis for this particular vector subspace. All right, so that is about the null space of T. Okay, one more definition. The definition states that definition doesn't state anything. Definition is of nullity of T. The dimension of the null space of T. Remember that null space is a subspace of the vector space V, and hence we can talk about the dimension of this particular vector space, vector subspace. So, the dimension of null space of T is called the nullity of T. Let me just underline, no, let me not underline it. So, this is called the nullity of T. Okay, so let us look at more examples now. No, let us not look at any more examples. Let us move ahead. Just like in the case of, if you recall, when we talked about linear independence, there was the notion of a spanning set. A linearly independent set had a corresponding notion of a spanning set. Similarly, the null space of a given linear transformation also has a corresponding notion of what is called as the range of T. So, that is the next thing that we will be exploring, range of a linear transformation T. So, let T from V to W again, Remember here again V and W are arbitrary vector spaces, be a linear transformation. And as the name suggests, we are going to define what is called as be a linear transformation. We are going to define what the range is. It's going to be the set theoretic range of T. Then the set TV, where V belongs to capital V, is called the range of T. And denoted R of T. So, we might be wondering why the range is being brought out. It's just the set theoretic range. Yes, that's true. This is just the set theoretic range. However, the properties of linear transformation forces the range of a linear transformation to be a vector subspace. So, let me just write that in a lemma, and I will leave this as an exercise. R of T is a subspace. A subspace of what? Remember that the vectors are mapped into W. So, this is a subspace, vector subspace of W. So, this is an exercise for you to check. I will not go into any examples. You should really go back to each and every one of the examples of linear transformations we have seen till now and try to calculate what the range of each of the linear transformations we defined is. So, observe that range of T is equal to W is the same as demanding that T is a surjective linear transformation. Okay. Just like how the dimension of the null space of T had a name, the corresponding notion of the range of T also has a name. So, definition: the dimension of R of T, where T from V to W is a linear transformation, is called the rank of T. So, from matrix theory, you might have heard of the word rank, and if you have heard of it, I should already break the suspense and tell you that this is related to that. We will come to that at a later date. Okay, so the dimensions of the null space and the dimension of the range space, they are related, and that is captured in what is called as the dimension theorem. So, let us now state the dimension theorem and give a proof of it. So, our next goal would be to state and prove the dimension theorem. So, observe one thing, all this while we were not demanding that our vector spaces V or W should be finite dimensional or not. We were, as of now, till now, we were giving a definition of linear transformation of null spaces, of nullity, of range, rank. All these things were being talked about without any reference to whether our vector spaces was finite dimensional. In this theorem, however, we will put a restriction on V. So, let V be a finite dimensional vector space. And T be a linear transformation from V to W. Then the dimension theorem states that the dimension of V is equal to rank of T plus the nullity of T. So let's look at a proof of this theorem. This proof is quite instructive. It really tells, it really shows us how the vectors v and w are interacting with each other through the map T. So this is one of those first cases where you will actually look at such statements. So let's look at a proof of this. So we know that dimension of V is finite. So let's give it a name. Dimension of V be equal to n. And we also know that null space of T is a subspace of V. So in particular, the dimension of V null space will be less than or equal to the dimension of V. And let's call that K. Nullity of T be equal to K, and we know that this is less than or equal to n. If K is equal to n, what is the meaning of that? It means that the null space is the entire vector space, which means that every vector is being mapped to the 0 vector, and therefore we know that the range is the 0 vector space, and the dimension of the 0 vector space is 0. So in that case, it's quite straightforward to check that dimension of V is equal to rank of T plus nullity of T. But we will not be doing this by induction, but nevertheless it was quite straightforward to show. That's why it was pinpointed. Let's try to prove this by a constructive approach. So we know that null space of T has a basis which has k elements. By one of the corollaries, we know that there is a basis and that it has to necessarily, by another corollary, it should necessarily have k elements. So let V1 up to Vk be a basis of null of T. We know that this is a vector subspace and we also now have a basis for that. We will extend this basis to a basis of V. Extending this to a basis of V, we get V1 to Vk, Vk plus 1 to Vn. What does it mean to extend a linearly independent set? Well, we could use the replacement theorem. We can start off with a basis of V and we have a linearly independent set of size k. Then we know that there is a subset of the basis of size n minus k. With this particular set, it will be the spanning set. Now the spanning set, a spanning set which has size n should necessarily be linearly independent again. So this is a basis which can be obtained that way. It's a corollary which we had done. I'm just recalling the proof of that particular thing. All right, so we extend it to get a basis of V. Okay. Now, if you look at TV1, it is 0. TV2 up to TVK, each of them is 0. So my claim is, okay, so what do we have to check? We know that nullity of T is equal to K. We know that dimension. So goal, just let's recall our goal so that we have a clear idea what to prove. We have to prove that dimension of V is equal to rank of T plus nullity of T. Or in other words, or rank of T should be equal to dimension of V minus nullity of T. But we know what these things in the right are. This is equal to n and this is equal to k. So we have to show that rank of T is equal to n minus k. But what is rank of T? Rank of T is the dimension of the range of T. So in other words, we need to get hold of n minus k vectors which will be a basis of our range of T. and that is going to be our next endeavor. In fact, let me write down a direct claim. T of V1 Vk plus 1 up to T of Vn, those vectors which we added to the basis of null space to obtain a basis of V. We look at the image of that. This is a basis of the range of T, which I will write as R of T. We already then have our result, because this set has size exactly equal to n minus k. Okay, so how to go about with a claim? So we have, with this claim, we have to show that this is both a spanning set and a linearly independent set. So let us start our work to show that it is a spanning set. So let W be an element of R of T. So we have to show that W can be written as a linear combination of T Vk plus 1 to T Vn. But what does it mean to say that V is in R of T? That means that it is the image of some vector V, i.e. there exists a vector V in capital V such that Tv is equal to W. That is precisely our definition of what R of T is. But we know that V1 to Vn, we should have called it a base. Okay, let's V1 to Vn is a basis, and therefore every vector of the vector space can be written as a linear combination of V1 to Vn. In fact, uniquely by one of the lemmas or propositions we had proved. So this implies there exists A1 to An such that V is equal to A1 V1 plus up to An Vn. But then Tv is equal to T of A1 V1 plus to An Vn. In fact, I should have written an AK Vk and AK plus 1 Vk plus 1 in the middle. I will do that in the next step. By the properties of linear transformation and an induction argument, you can show that this is equal to T of A1 V1 plus T of A2 V2 plus up to T of An Vn, and then you can show that this is equal to A1 T V1 plus A2 T V2 plus up to AK T Vk plus AK plus 1 T Vk plus 1 plus up to An T Vn. But what is Tv1, Tv2 up to Tvk? Recall that V1, V2 up to Vk is a basis of the null space of T. So this is our 0 vector. Tv2 is our 0 vector, Tvk is our 0 vector, all these are 0 vectors. So this is the 0 vector of W, and hence this is equal to Tak plus 1, Tvk plus 1 plus up to An Tvn. That is establishing the claim that, or the fact that Tvk plus 1 up to Tvn, this set is a spanning set. Of R of T. Now, if we show that it is linearly independent, we have proved our theorem. So, how do we prove that it is linearly independent? We take a linear combination which is equal to 0 and try to prove that its coefficients are all equal to 0, and hence it is linearly independent. So, let's now use some other notation so that it's not confusing here. Let B k plus 1, so linear independence. This is what we are next trying to prove. Let Bk plus 1 Tvk plus 1 plus up to Bn Tvn be equal to 0. This 0 is a 0 vector of W, and we have to show that Bk plus 1 to Bn, each of these scalars is necessarily equal to 0. But by the same argument above, going in the opposite direction, this implies that T of Bk plus 1 Vk plus 1 plus up to Bn Vn is equal to 0. Why is that the case? Because these two are equal. That is what we know by the very definition of linear transformations. So, this is equal to 0. But what is the meaning of some vector being sent to the 0 vector by a linear transformation? It means that it belongs to the null space of T. So, this implies that Bk plus 1, Vk plus 1 plus up to Vn belongs to the null space of T by the very definition of what null of T is. But every vector of null of T can be written as a linear combination of its basis vectors of, if you have a basis already, which we have. So, this implies that there exist scalars B1 to say Bk such that this vector is equal to B1 V1 plus up to Vk Vk. Any element has to be for some Bi's, for some B1, B2 up to Bk. Rewriting this, we have minus of B1, V1 plus minus of Bk, Vk plus Bk plus 1, Vk plus 1 plus Bn, Vn is equal to 0. So, remember that the 0 here is the 0 vector in V. The 0 here was the 0 vector in W. So, I have stopped writing all the subscripts. It is for you to understand from the context that this is the 0 vector in V here, what we have just written. Okay, we know now that V1 to Vn is a basis of capital V, and this forces, because of linear independence, this forces each of these Bi's to be 0. In particular, this implies that Bk plus 1 up to Bn is equal to 0, and that is precisely what we wanted. See, observe that we wanted to establish that this forces our coefficients to be equal to 0. This implies hence that Tvk plus 1 up to Tvn is linearly independent. And that implies rank of T is equal to n minus k, and that completes our proof. So, this is one of the most beautiful examples of how a linear transformation helps us take information from our domain to our range and back. As you can see, the linear independence of V1, V2 up to Vn was used to prove that the vectors Tvk plus 1 to Tvn, which are vectors in W, are linearly independent. And similarly, many such examples of how T takes properties of vectors in V to the corresponding vectors in W can be seen here. Okay. So, this is a very powerful result actually, just to give you an indicator of how powerful this is. Let us look at this example. So, let D be the map from P3 of R to P2 of R, where D is our differentiation map. D of P of x is equal to P prime of x. Then observe what is happening. Then dimension of our P3 of R, we needed it to be a finite dimensional vector space. In this case, this is equal to 4. We already saw what the null space of the differentiation operator is, differentiation linear transformation is. The dimension there will be equal to the dimension of the constant polynomials as a subspace. So, null space of D is the set of all C in R, the constant polynomials, and nullity hence is equal to 1. R has dimension 1 over itself. So it's you can check that this is the basis is given by any non-zero real number, and this implies our rank of D in this case, D is equal to 4 minus 1, which is equal to 3. But observe that this is equal to the dimension of P2 of R, which indicates that D is a surjective mapper. Basically, the range of D hence is equal to P2 of R entirely. So, what does it mean to say that? This means that every degree 2 polynomial can be realized as the derivative of a degree 3 polynomial. We know this by our information, our knowledge from calculus, but this is a linear algebra way of obtaining something similar. Of course, some calculus was used here. Yes, so let me stop by giving another proposition, which is maybe not a proposition, let me just call it a corollary. It's a corollary to the dimension theorem. Let V and W be finite dimensional vector spaces. V and W be finite dimensional vector spaces such that dimension of V is equal to the dimension of W. Then suppose further let T from V to W be a linear transformation. The conclusion is that then T is injective if and only if T is surjective. T is injective if and only if T is surjective. So, let us look at a proof. This actually is a direct consequence of our dimension theorem. So, by the dimension theorem, before we even enter into, okay, let us look at the direction. Let us assume that T is injective, let us prove that T is surjective. T is injective implies that the null space of T is the 0 space. That was a theorem which we proved some time back, and therefore the nullity of T is equal to 0. So, the dimension theorem tells us that dimension of V is equal to the rank of T, but dimension of V is equal to the dimension of W by the very hypothesis of this corollary. So, this is equal to the dimension of W. So, we have a vector subspace of W which has the same dimension as W, and this implies the range of T is equal to W, which implies T is surjective. Alright, so can we do the same thing in the opposite direction? If I am to put green arrow, what does it mean? So, T is surjective implies range of T is equal to the range of W. Range of T is equal to the range of W implies that rank of T is equal to the dimension of W is equal to the dimension of V. But that implies by the rank nullity or the dimension theorem, this implies that the nullity of T is equal to 0, which implies